Okay, here's a continuation of our Codeology series on Article 250. These are some examples that we want to do. And so this is examples number 1, and we're going to specifically focus on systems. The intent of these videos is an opportunity for you to have the code book on one hand and to look through some of the code book and follow along as we talk about specific code articles. So first of all, we need to talk a little bit about some of the terms that we're going to deal with as we're looking at grounding and bonding under Article 250. Now these terms are defined in Article 100 under definitions, but we want to kind of just look at these visually here. Quiz yourself as we go through this and see if you can get these right. Our first term that we want to look at is the grounding electrode. Now be careful on this one because this one's often misunderstood. The grounding electrode is in fact the piece of steel or the ground rod or the water main. There's many different types of grounding electrodes. Now those are discussed in Article 250 quite extensively. We're not going to get into that here, but if you want to look in Article 250 under Part 3, it talks a lot about the grounding electrode and the grounding electrode system. The next one here is the GEC. Now we have a lot of initials and a lot of shortened names for this. This in fact stands for the grounding electrode conductor. Well, as you guessed it, the grounding electrode conductor is what connects the grounding electrode to our service or our system, and that would be represented by the wire here in V, this wire that goes from the building steel to our system. The next one is the grounded conductor. Again, this is one that gets misinterpreted a lot because we always talk about the ground and we use that very loosely, but the grounded conductor according to the code is in fact the white wire or the neutral. We often call it the neutral, but that in the code is going to be discussed as the grounded conductor because what it does is it actually is a grounded conductor because of what we have, the MBJ or the SBJ. Now that's check yourself on this one, but that's going to be this shown as X. And that actually is the jumper, the main bonding jumper or the system bonding jumper that jumpers between our grounded electrode and our grounded conductor. So this conductor X that ties the two bus bars here together at our system main disconnect is the main bonding jumper or the system bonding jumper. So these terms are important to understand as we ask questions and understand what needs to happen. So just as a quick review to understand the terms, we talked about the grounding electrode, the grounding electrode conductor or the GEC, the grounded conductor, which we often call the neutral, the main bonding jumper, MBJ, or system bonding jumper, SBJ. And then in Article 250, under 250.30, it introduces a supply side bonding jumper, so you can read a little bit about that. One of the first things that we need to do is determine our system. In Article 250, under Part 2, under Systems, it has several definitions. The first one it starts out with is 250.24, which is a service-supplied alternating current system. This is the one that we're going to be most familiar with because when a utility supplies us with service, that's a service-supplied AC system. Also, we have in 250.30 a system that's described as a separately derived system. This is typically when we have a transformer and then we now create a separately derived system. For instance, if we have a service, Lady 277, and then we put a transformer in the building to drop that voltage down to like a 208, 120, that would be a separately derived system. 250.32 addresses buildings or structures that are supplied by a feeder or branch circuit, so it describes these as a system. And then 250.34 also addresses a portable and vehicle mounted generator, so a generator is also a type of system. Okay, let's look at our first example here. One of our examples that we have here talks about that we have a panel that has a 400 amp breaker. A couple of parallel conduits feed it with that each have two 3/0 conductors for the ungrounded conductors. Most of the loads are 240 volt without neutrals. What's the smallest neutral that can be installed? Anytime we look at a story problem or a description of a scenario here, one of the first things we need to do is start to identify some of the key terms that we're looking for. So as we see this, we see that one of the key terms is service. So we are going to assume that this is a service system. It has parallel conduits, so we need to pay attention to that. And the question itself is asking for the smallest neutral that can be installed. So let's look at some of the details that we need to understand now. Some of the pertinent information that we need to understand when we're looking for a neutral or a grounded conductor is that must be sized sufficient to carry the load. Well, that sounds pretty simple, but when it's asking for minimum sizes, sometimes we have an option. Sometimes we look at something and the code is going to require that it be a minimum size that is actually larger than what is needed to carry the load. And sometimes the code is going to specify that it's smaller than what might be necessary to carry the load. So it's important for us to know that option exists, and so if we have a load that's greater than what the code says, we have to follow we have to have an ampacity to carry the load. And service and feeder grounded conductors are sometimes treated different. In Article 215, it addresses feeders, and so we need to pay attention to that. If we're looking for a feeder, if the question's asking us for a feeder that's not a service, then we might need to go someplace besides Article 250. So Article 250 for the grounded conductor is going to talk about the service conductors. Some of the pertinent codes that we need to look for. We're going to start with 250.24 because this is, on this example, it stated that it was a service. So as we look at 250.24, under Section A and Section B, we'll see that those really aren't applicable to this one. We're not talking about the connections, nor are we talking about the main bonding jumper. However, when we move to Section C, the grounded conductor is what we are talking about. But don't get too excited because it tells us in here in C1 to go to Table 250.66. This is a mistake that a lot of electricians make, is they automatically go to 250.66 or 250.122 because they're accustomed to going to those tables. So we need to look and see under 250.24C2 is where it talks about the parallel conductors in two or more raceways, which is what our problem addresses. So 250.24C2, parallel conductors in two or more raceways, it states if the ungrounded service conductors are installed in parallel in two or more raceways, the grounded conductor shall also be installed in parallel. The size of the grounded conductor in each raceway shall be based on the total circular mil of the parallel ungrounded conductors in the raceway, as indicated in 250.24C1, but not smaller than 1/0. And then it references 310.10, which talks about grounded conductors in parallel. So we can go to 250.66 and make our calculations, but if our calculations end up being less than a 1/0 conductor, then a 1/0 conductor is the minimum as long as we're in parallel. And 310.10H also basically states that if we're going to parallel conductors, then 1/0 is the minimum for the grounded conductors or for the ungrounded conductors as well. So if we have parallel conductors, then we have this little 1/0 rule that we need to pay attention to, and that's really what this example is illustrating. So let's look at another example, example number 2. So at this one, we just have a problem that is stated: a switchgear is fed from a transformer with a 350 kc mil wire and 4 parallel conduits. The smallest size system bonding jumper. So I've highlighted the key words here. So fed from a transformer. So we're going to assume that that's a non-service, that it's a separately derived system. We've got the size, and we're looking for the size of the system bonding jumper. So here's some of the quick pertinent information. The main bonding jumper and system bonding jumper, because they're something that ties to the overall system, they relate to the total amperage and not just the size of a single conductor. Where with the grounded conductor, we were just talking about the size of a conductor in the raceway. This one we have to calculate the total amperage of the entire system. So 250.24 for systems, or for services, and 250.30 for separately derived systems, they both reference 250.28 for the main bonding jumper and system bonding jumper. It is helpful to track through for the specified system, though, because they will reference in 250.24 and 250.30, they will reference us and point us to 250.28 when it comes to the MBJ and SBJ, which is kind of helpful. So, but we're going to jump straight to 250.28, which tells us how to size this conductor. So basically, in 250.28 D1, it says to size it according to 250.66, the table. So we have to derive the size of the conductor, and when it's larger than 1100 kc mil, then we calculate the size with a 12.5% rule. And then we can go to Table 8 in Chapter 9 for the conductor area properties to calculate. So let's look at this example. We had 4 350 kc mil conductors, so the overall service, or not service, the overall system size is a 1400 kc mil. So we take that 1400 kc mil and multiply it by 12.5%, or 0.125, and that gives us 175 kc mil. So we can go to our Table 8, in Chapter 9, and look under 175 kc mil to find out what wire size that is. You can find out 175,000 in Table 8, Chapter 9 is in fact a 4/0 wire, so that becomes the size of our in this particular example. Now quickly, let's take a minute and practice using our grounded electrode conductor. So as we look at our grounded electrode conductor, so this is in Part 3 of Article 250, where it talks about the grounding electrode conductor and the grounding electrode system. And as we follow through, and we're now trying to find the size in order to size our grounding electrode conductor, we end up at 250.66. However, it's interesting to note A through C gives you exceptions for the sizing of that grounding electrode conductor. So as we bring our grounding electrode conductor to something such as a ground rod, it actually tells us that the maximum size is a number 6 copper for that grounding electrode conductor. However, for things such as building steel and everything else that are not covered by those exceptions, then we go to Table 250.66. And again, we want to note that our grounding electrode conductor is the size of the entire system. So we might have to derive that size of that system, not just an individual conductor. So when we have parallel conductors, we have to pay specific attention to this. So just as a recap, again, we'll continue to expand this series. We hope that you'll find opportunities to practice. Your confidence on the test is going to come from practice. So we encourage you to use the index and tabs to help you move sections faster. We would like for you to get used to reading the entire reference as well as the exceptions and see how it fits in the big picture, not just as a tab note or an index note. So stay with us and keep practicing and keep reading that code.